All right, today we are diving into one of the most critical, but honestly most overlooked decisions when you're building out the infrastructure that's going to power AI, and that is how do you keep it cool? We're going to break down two totally different philosophies where the choice you make has these massive consequences for reliability and, you guessed it, cost. So let's get right into it. When we think about what's holding AI back, our minds usually go to things like algorithms or processing power or finding enough data. But what if the biggest bottleneck, the single greatest physical barrier to that next big leap, isn't any of those things? That's right, heat. Every single calculation, every little bit of machine learning magic generates a tremendous amount of heat. And managing that heat, that's the real engineering battle. If you fail at this, the most advanced AI cluster on the planet just becomes a very, very expensive room heater. And right at the center of this whole fight is this device, the Coolant Distribution Unit, or CDU. The best way to think of it is as the heart of the entire cooling system. It's what pumps the life-sustaining coolant to all the servers, making sure they can run at full tilt without, melting down. Its reliability is absolutely everything. Okay, so how do you actually deploy this critical piece of hardware? Well, it really boils down to two fundamentally different ways of thinking. One philosophy is all about centralized heavy-duty engineering. The other is about distributed, easy-to-deploy convenience. And this is where things get really interesting. So on one side, you've got the in-row CDU. This is a floor-mounted beast, a centralized workhorse that's built to serve a whole row of servers at once. And on the other side, you've got the in-rack CDU. This is a much smaller unit that actually lives inside a single server rack. So one is a big architectural decision, and the other feels more like a component you just kind of plug in. Now, here's the thing that's so important to understand. The core technology, the pumps, the heat exchangers, it's all basically the same stuff. This is not a debate about who has better parts. It is 100% about where you decide to put those parts. And as we're about to see, that single architectural decision has a massive domino effect on everything that follows. So let's start with the most important claim of all, redundancy. That promise of nonstop, 24/7 operation. This is where a major myth has really taken hold in the industry, and it all revolves around one simple-sounding question. The marketing for in-rack CDUs just loves to talk about their dual pumps. And hey, it sounds great, right? 2 pumps has to be better than 1. But does having 2 pumps in that little box actually give you true system-level redundancy? Let's peel back the marketing and look at the actual engineering. And boom, here it is. This chart shows the whole problem in a nutshell. See, true redundancy isn't about one component. It's about the entire system. An in-row setup lets you have a whole extra CDU on standby. That's what we call N+1 redundancy. So you get backup pumps, a backup heat exchanger, backup controls, the whole shebang. The in-rack unit, yeah, it's got 2 pumps, but that's it. Everything else is a single point of failure, just waiting to ruin your day. So here's the bottom line. If that single heat exchanger in an in-rack CDU fails, your entire rack of servers goes down. If its single little control system has a glitch, your rack goes down. If one of its valves fails, I think you get the picture. Those dual pumps can't do a thing to save you. The entire rack's operation is balanced on a razor's edge. Okay, so we don't just have to take my word for it. How do we formally measure this stuff? Well, we can turn to the industry's gold standard for data center reliability, the Uptime Institute's tier standard. Let's put these two architectures to the test and see how they really stack up. First up is Tier 3. This is a huge benchmark for any serious data center. It's called concurrently maintainable, which is a fancy way of saying you can take any single piece of your cooling equipment offline for maintenance or repair, and your servers just keep on humming without a single interruption. The key to this is having N+1. At least one independent backup unit ready to go. And when we run our 2 contenders through the Tier 3 test, well, the result is pretty brutal. The in-row architecture, because you can have that backup N+1 unit, it checks every single box, no problem. The in-rack model, it fails completely, across the board. You simply cannot take it offline for maintenance without shutting down the entire rack of servers it's supposed to be protecting. The official verdict from the source material is blunt, and there's no ambiguity here. The in-rack architecture fundamentally fails the intent of a Tier 3 design. So for any facility that's claiming to be Tier 3 reliable, this is a complete non-starter. But hey, let's raise the stakes even higher. Let's talk Tier 4, fault tolerant. This is the absolute peak of data center design. This means your system can survive any single unplanned failure, a pump suddenly seizing, a controller crashing, and keep operating without a single blip. This requires full 2N, or two completely independent redundant systems. And against this highest standard, the difference becomes even more crystal clear. An in-row system can be properly designed with totally separate A and B cooling paths to achieve that 2N fault tolerance. The in-rack CDU, with all those single points of failure we talked about, it's not even in the same league. It doesn't get close. And this is the final nail in the coffin on this subject. It's not just that the in-rack model fails the Tier 4 test, it is structurally incapable of ever passing it. The very design philosophy, cramming the entire cooling system inside the IT rack, makes true fault tolerance a physical impossibility. So, the engineering cases, I think we can agree, pretty open and shut. But what about the practical, day-to-day side of things? The main argument you hear for in-rack is always about convenience. But that convenience comes with some really staggering hidden costs that pop up over the life of the data center. Just take a look at this number. For a pretty modest 40-rack AI cluster that uses in-rack CDUs with dual pumps, your maintenance team is now on the hook for over 80 different pumps. Think about that. 80 potential points of failure, 80 things to monitor, 80 items on your maintenance schedule. It's an operational nightmare. Now, let's flip that and look at an in-row deployment that's cooling the exact same 40 racks. You're maybe looking at 4 to 6 pumps total. The difference in operational simplicity is just night and day. We're talking fewer alarms, way fewer spare parts to keep in stock, and a dramatically lower risk of somebody making a mistake during maintenance. But there's another cost, and this one is a really big one: physical space. Every single one of those in-rack CDUs eats up valuable real estate inside the server rack. We're talking anywhere from 4 to 8 of those rack units, or Us. And that is not just empty space. In the world of high-density AI, every single U of rack space is potential revenue. By putting your cooling infrastructure inside the money-making space, you are directly sacrificing compute density. You're sacrificing your ability to generate income from that footprint. It's a business trade-off that, frankly, makes almost no sense. So when you pull all of this together, the fake redundancy, the failure to meet industry standards, the insane operational complexity, and the lost revenue, the picture becomes incredibly clear. This choice isn't just a technical detail, it's a strategic one. And this brings us to the ultimate conclusion from the source material, and it is such a powerful statement. For anyone who is serious about building scalable, mission-critical infrastructure for AI, this isn't really a choice. The supposed convenience of the in-rack model is just an illusion, and it comes at the unacceptable price of resiliency and being ready for the future. So the final question really is for anyone out there designing, building, or investing in the future of computing. It's a choice between the easy path, the convenient path that's just littered with hidden risks, and the engineered path, the one that's built on the conviction that reliability is simply not negotiable. The only real question is, which path are you on?